two more tests today. And actually now, so we have three tests. One for divergence only, the nth term test. One for convergence only, the alternate series test. And then the geometric series test, which does both convergence and divergence. Today, we're going to have two more tests, and they test for both as well. So we're going to get into this next unit where our tests are going to be more useful, generally speaking. They do have specific conditions that need to exist first, but like the geometric series test, it has to be a geometric series. The integral test can be used for just about any series. The p-series test is a specific type of test. So anyway, this is on page 216 in your book. We're going to start with the integral test, and then we'll talk about the p-series test. So you can either screenshot it from your book or you can take a picture, but you need this in your notes. So I'll give you a second to do that. Okay, so here is, we do have some conditions like I mentioned. So in order to use the integral test, we have some function. It must be positive, continuous, and decreasing for all x values greater than or equal to 1. So that's important to pay attention to. If we're talking about other x values that are less than 1, it doesn't really matter. It only applies when we're looking at x greater than or equal to 1. And so this sequence, a sub n, the terms a sub n is equal to f of n when we substitute n in for x. Then, if this is true, then the series and the integral either both converge or they both diverge. So what we're going to be doing here, we're going to have some series. We're going to integrate it, and look, it's an improper integral. Remember improper integrals when one of the limits is infinity. If this integral has a value, then it's convergent. If this integral does not go to a value, it goes to infinity, or negative infinity for that matter, then it diverges. Please understand this though. The sum does not equal whatever the value is for the integral. This is really important. If they actually ask you for the sum, then we have to use some other way to come up with that sum. But those two things are not equal. The sum and the integral are not equal to each other. But what happens with the integral makes a determination about what happens with the series. Okay? That is the integral test. One thing that looking at your test the other day, and I'm going to keep emphasizing this because when we get to the exam, it's really important to state that these conditions exist and to test for them, like to check it out. And in some cases, writing some of this out, testing some of the values in the series out to make sure this is true is important to do. Most of the time, I believe if you just state that, that's good enough. But remember, if these things are not all true, you can't use this test. And as now we're going to add two more tests to your list of 3 tests, so we're up to 5 tests after today. And then we still have a few more tests after that. The trick is going to be, especially on the exam, is to determine which test to use when. And we'll continue to work on that before the test. So on the same page, we're going to go through these 3 examples. So you can, again, either take a picture of that or screenshot it from a book, up to you. Okay, so here's what we're saying. And they tell us for these examples to use the integral test. So of course, in your book, in the directions in the homework, they will often tell you which test to use because we're still getting practiced at this, trying to get good at this. So the first thing we have to figure out, is this thing positive? All right, when I plug 1 in and 2 in, all these values stay positive, especially since we're squaring it. So we're good on the being positive. Is it decreasing? So as n increases, so as this bottom increases, because this will be 1 squared, 2 squared, 3 squared plus 1, 4 squared. This bottom, as n goes up, the bottom goes up, which means the fraction goes down. Okay. And then, again, for all the x values, 1 or more. And then, same thing, this is continuous. The only way this could not be continuous is if somehow n squared equaled -1, and then we got a 0 there. But since these are all going to be values, it's going to be continuous. So it's simple enough to go through that. And so if we just state f of x is positive, continuous, and decreasing for x greater than or equal to 1, that is good enough. But you do want to do that check, and just to make sure, okay? So then what's going to happen is we're going to integrate this, okay? And because of the fact that the upper limit is infinity, we are talking about an indefinite integral, okay?
Do you have to say for x is greater than or equal to 1?
You do. And you could also say f of n or n greater than or equal to 1. I think I said it before too. Improper integral. This is an improper integral when the limit is either continuous somewhere or one of the limits of integration is infinity or negative infinity. All right. Whew. Now, this should look familiar to you. There's not a special trick to integrate this. Do you remember what this is when we integrate this, what it is? Say it. Arctangent. Very good. This is the arctangent. And so that's how those kinds of things are going to get worked into your problems, right? They're not going to ask you specifically to integrate arctangent or arc cosine or arc sine. You're going to have to recognize it like that. So when I integrate this, what I end up with is a limit of b, and we maybe even used t before, but whatever this variable is, it doesn't really matter. So this is the arctangent of x from 1 to b. Well, we have to know how to do that. Okay. So as b approaches infinity, now here's another thing. Do we remember what happens, what our range of values can be for the arctangent? Remember that's restricted. Nope, it is not -1 to 1.
Then I think cosine pi over 2 to pi over 2.
Cosine, yeah, but when we talk about the arctangent, there's a restricted domain that we can use. And because it's going to go to infinity, I'm looking for the highest value here. The highest value that's allowed for the arctangent. It's pi over 2. It goes from negative pi over 2 to pi over 2. What is the arctangent of 1? What angle are we talking about there? In radians. Pi over 4, very good. Okay. So what this really is pi over 2 minus pi over 4. Now, of course we could figure that out. But we don't have to. Is this a value? Is this a number? Sure. This is pi over 4. So the integral of this equals an actual value, which means the sum of this will equal an actual value. And all that means is it's convergent. And so this is good enough. You can stop there and just say, okay, it converges by the integral test. Because when I integrate this, I actually get a value. That means the sum will also converge. It doesn't tell us what it will converge to, but it just will tell us that it converges. Okay, that's how the integral test works. All right, let's look at this next one. Is this positive? This one starts at n equals 2. Is this positive? Natural log is going to be positive, right? Obviously, that's positive. Is there ever discontinuous, okay, obviously if this was 0, that'd be a problem, but that can't happen. That's why they start at 2, right? Because if the natural log of 1, that is 0. So that would be a problem, but they forced us to start beyond that. So we're continuous, we're positive. These numbers, even though the natural log grows slower as n gets bigger, it's still growing. And of course, as n gets bigger, this is also growing. Long story short, as n gets bigger, this whole denominator gets bigger, which means the entire fraction gets smaller. So our conditions are met. It is positive, continuous, and decreasing. Again, in this case, we have an improper integral because our upper limit is infinity. And so this is what we're talking about. Okay. Just replacing the n with x. How are we going to integrate this? How? What are we going to, what's u going to be? Yeah, natural log x. Because right here, there's my derivative. The natural log, the derivative of the natural log is 1 over x. So u is natural log, du is 1 over x. So that's pretty straightforward, right? So this really is the integral of 1 over u, du. But then one of the things, of course, they test for on the exam, it's an essential knowledge piece, is replacing the limits that we started with, the limits of integration, with some new limits of integration. So I'm going to plug b in here for x. So this will be natural log of b. I'm going to plug 2 in for x, and this will be natural log of 2. Okay, so again, when we integrate that, that's the natural log of the absolute value. Okay, and so then that's where my integration changes, the substitution changes the integration limits, and then I integrate that. Okay, so my natural log of the absolute value of u, and we'll see if that's necessary here in a minute. And you're never gonna be in trouble by leaving the absolute value in there. Okay, so I'm going to integrate from natural log of 2 to natural log of b. Bless you, by the way. And so here we are. Okay, natural log of the natural log. This, of course, is an actual value, whatever it is. What about this? If I think about the natural log of infinity, it's infinity. This is going to grow without bound. So the limit of all of this approaches infinity. Remember, don't write equals infinity. So does the limit have a value? It does not. It never approaches anything. Okay, it grows without bound, which means that this sum also does not have there is no sum for this. Okay, it will continue to grow and grow and grow. So therefore, we can say that this diverges by the integral test. Again, this is only the second test that we can show for both. Okay. All right, let's look at the last one. Now, this one is tricky, and we're going to talk about this one more and more and more. Because if we think about it, what's happening to the terms as n grows? As n grows forever, what happens to the terms? Smaller and smaller and smaller and smaller until they basically approach nothing. But yet, and we can look at that proof another day, we're going to find out something interesting here. So the terms are getting smaller, so there's my decreasing. They're positive, and there's no hole. The only way there could be a hole is would be n equals 0. So we're good there. Our conditions are good. Okay, we've already looked at the limit of this, but we'll keep, or the integral of this. We'll let's go on with it. Okay, so I set up my improper integral. And when we integrate 1 over x, of course, we get the natural log. And that's from 1 to b. Sub it in. Okay, what happens with this one? Where does this go? It goes to infinity. Okay, which means, again, this diverges by the end of the test. Okay, so even though the terms get really, really close to 0, the sum never actually gets to a particular number, which leads us into our next test. Because this is a very special series. It has a name even, this particular one. And we're going to talk about it here on the next slide. Okay? Questions so far? All right, so did I skip one? No. We need to talk about the P-series test. The P-series and the harmonic series. Okay? So notice here, if I have 1 over n to the p, if p is a positive constant, then this is called a P-series. Right? The p is the power, and that's what p stands for, I would guess. Power series, a different kind of power series. The harmonic series is the one that I was just talking about. That's the special one that we just looked at on the other page, and we'll talk about that here a little bit more. The P-series test, if the conditions exist, right, if it is actually a P-series, can test for convergence and divergence. It's all based on what the value of P is. If the power is greater than 1, notice not or equal to, greater than 1, then the P-series converges. So whenever this power is greater than 1, then it will be convergent. If this power, since we talked about a positive constant, is between 0 and 1, because it can't be equal to 0, right? It's got to be a little bigger than 0. And it can equal 1, then the series diverges. So in other words, on the last page, we talked about 1 over n to the first, basically. That is the harmonic series. Okay? So this was the last example. That's why I wrote this example 3 that we did. This was the harmonic series. The harmonic series always diverges. You are allowed to say on the exam, it's a harmonic series divergent. You don't have to say that it's a P-series because of the P-series test. You can just, we're allowed to know that the harmonic series always diverges. Why it's called the harmonic series, I think it has something to do with sound waves, and it has something to do with, like, when you pluck a string on a guitar, you know, the initial pluck will give it certain amplitude, and then as it vibrates, the amplitude of the guitar string gets smaller, smaller, and smaller. I think that has something to do with why they called it that. But I'm not 100% sure. If you'd like to research that, you're welcome to do that. Let's go through a couple examples of P-series, and we'll kind of go from there, okay? So, we have 2 examples that we're going to look at. And again, in the book, they're going to tell you what series to use. In general, when we get there, by the end of this course, which content-wise is not very far away, you're just going to be given a series, and you're going to have to choose which test to use. And that's toward the end of this unit, we're going to talk really about how to do that. Now, when you initially look at something like this, maybe you don't see that it is a P-series. Same with this one. I want to go through how to do that analysis. Because what we have to determine is what is P, what is the power. Because if the power is between 0 and 1 inclusive, then it's going to diverge. If it's greater than 1, then it's going to converge. So we have to determine what the P is. Now, the best way to do that here is to look at a couple of these terms and make some decisions, right? Because the square root of 2 is 2 to what power? 1/2. So this is really 2 to the first times 2 to the 1/2, which is what? 2 to the 3/2, okay? So our initial thought is, okay, P is 3 over 2. But let's test one more term just to be sure. So this is 3 times 3 to the 1/2. 1 plus 1/2 is 3/2. So we're confident now. P is 3/2, which is greater than 1. Therefore, okay, so this is what the series really is. If I was to write it in sigma notation, this is what the series really is. Yeah, and starts at 1. So when we state that it's convergent, what we're going to say, we're going to state, first of all, 3/2 is greater than 1. That's sort of the evidence. That's what I'm using to draw my conclusion. So you want to state that. And then you can say that it converges by the p-series test. That's enough. This is important. Don't just assume this part. Literally state it. Convince the reader that you know why it converges. Don't just look at it and say, oh, okay, I know this is bigger than 1, so it has to converge. Give the evidence. Show that you know what you're talking about. That's important. And that's something we'll continue to get better at and better at. All right, now this one over here is a little goofy, right? This doesn't look like a p-series test at all. There's not even a fraction here. But is there? So this is n to the 3rd. How would I rewrite this using rational exponents? N to the what? Negative 11/3. Okay. Well, 3 plus negative 11/3. That's really 9/3. 9 plus negative 11. Negative 2. So this is negative 2/3, which means I can just slide it to the bottom. 2/3 bigger than 1 or less than 1? Less than 1. So state that. Okay, it's in between, right? It's in between 0 and 1, because these are the conditions for the p-series test. So that's the proof. So this is going to diverge by the p-series test. So this is like the final thing before your conclusion, right? I've done all the work. Here's all the evidence. Last step before I make my conclusion.